Yes. You can start it.
Can everyone see the screen?
It's visible. It's visible.
So I'm sure that you have all heard about vectors from class 11. We have heard in physics, in coordinate geometry. So can you give me some examples of vectors?
I can.
Yeah, give me some. Yeah, velocity, force, right? So yeah, so how do we represent it in physics? We write it using something like this. Yeah. So what does this indicate? This is the magnitude and this is my direction. So in physics, it is something which has a magnitude and a direction. And in mathematics, we have learned it as a directed ray from my origin. And yeah, someone said an ordered n tuple. That's what I'll come to. So the coordinate of a point, it is an ordered pair or an ordered triplet. So this ordered pair or triplet, we can just extend it to something as a general n tuple of n real numbers that we call as a vector in the n dimension. We cannot visualize a dimension greater than 3, but this is the concept that we are extending a triplet or a pair to a general n tuple of real numbers. Also, one more way we can visualize it is this set of numbers from
Yeah.
1 to n.
पहली line पे नहीं, third point का.
Sorry? Did someone say?
That was my mistake.
So a function from this set to R. We will get n many real numbers, right? So we arrange those n real numbers and we get n ordered tuple. So that we call as Rn, which we will formally define here. The set of all ordered n tuples like this, where each xi is a real number, that is the n-dimensional Euclidean space or Rn. So why Rn? Because it is just a short form of all functions from the set 1 to n to R. So we can see practical examples. Profit or loss of n companies. It can take any real value, negative, positive. Then solutions of a system of homogeneous linear equations. So we can firstly see that the solution of this will not be unique because there are 3 variables, 2 equations. But we know how to solve this, right? Ax equal to 0. Now, what if we replace this 0 with something else, say 1? Will it still be a vector or a vector space? What do you think? Suppose this is 1.
It has to be a matrix on the right hand side.
Can you say it a bit louder?
It has to be a matrix on the right hand side.
Yeah, it is a matrix. Ax equal to, this is 0. That I'm saying it is a vector space. But if it is 1, what will happen? Suppose we have 2 solutions, x1, x2, where ax1 is 1, ax2 is 2. Ax2 is also 1. Now, if we add those two, it will not give the solution as 1, right? Ax1 plus ax2 will not be 1. So it is not closed under the plus operation. So it cannot be a vector space. So only if it is a homogeneous linear equation, it will form. Okay. If you don't understand anything, please just ask a question.
Can you please repeat?
This homogeneous thing.
Ma'am, actually, what is that AX?
How do you solve this kind of an equation? You write a matrix, the coefficient matrix 1, 1, 2, 1, 1. Then the variables equal
Ma'am,
to.
actually, I don't know that matrix method.
Oh, you haven't learned. Okay, so to solve this equation, this is an easy way. You can just replace and everything. But-
Yes, ma'am, by substitution.
Yeah, but to solve a general linear equation, if there are n many equations, it is difficult to solve it with substitution and everything. So just to make it systematic, we write a matrix with the coefficients. Coefficient here is 1, 1, and 2. And here 1, 1, coefficient of x3 is 0. So this is my coefficient matrix. And here is x1, x2, x3. That is equal to 0, the 0 matrix. So this only we solve with by taking all inverse and everything. But I'm saying that this set of the solutions of such an equation, that will be a three or an ordered triplet, right? x1, x2, x3, where it is not unique. There will be more than one solution, but it will form a vector space. I know I haven't defined it yet, but it will form a vector space if it is a homogeneous equation. That is if there is 0 here. Otherwise, it will not be closed under this plus.
Ma'am, but what is vector space actually?
Yeah, that I am defining in the next slide.
Okay.
Before that, we need to just recall the operations. You have all learned about vectors, right? In 11 and 12.
Ma'am, actually the number of solutions of that equation, because they will there will be infinite or many, because the equations are 2 only but variables are 3, so that number of solutions we are defining as vector space.
No, number of solutions is not defining. I'm saying set of all the solutions will form a vector space. Okay. Now, I will define vector space in the next slide. First, just recall the operations. These are the operations we can do. So we have seen in R2 and R3, we know parallelogram law for addition. We can add two vectors. We can multiply it. Say we want to double it, then 2v will be just double. So these are the two operations. So in a general Rn, we can define addition of two vectors like this, just coordinate-wise addition, and scalar multiplication, coordinate-wise scalar multiplication. One more thing, there will always be a 0 vector. In Rn, it is very obvious. It is the all coordinates 0. And now this set of all the vectors together with these operations and a 0 vector is what we call vector space. So I'm saying I'm defining vector space over R, that is the real vector space. But generally, we will define it over something called a field, which is a more general set of these scalar numbers. So now, this is my formal definition of vector space. There may be a lot of symbols which is making it look very complicated, but it is nothing. It is just a definition of very elementary things which we have learned since like childhood. So vector space, so all these things you will come across: vector space, group, ring, field. These are nothing but just some set with certain operations and properties. So vector space is a set with the binary operations plus and dot. So we know what binary operation is, right? If there is anyone who doesn't know binary operation, then please tell me. So this plus is from V cross V to V, that is addition, and dot is from R cross V to V, that is scalar multiplication, which satisfies these properties. So this addition and multiplication is a very abstract thing. So in R, we know, in R or complex or rational numbers, we know that what plus and dot exactly are. But we will see examples where this plus may not be the plus that we know about. So it is just a symbol for now. In the definition, it is nothing but a symbol with these properties. So what are the properties? This V plus forms an abelian group. Abelian is just a fancy word for commutative. And what is group? Again, it is a set with some binary operation that satisfies these three properties. Not this property is not defining for a group. If it is there, then it is a commutative or an abelian group. So first property is associativity, then existence of identity. There exists an element called zero element for which this holds. Then existence of an inverse, which is called negative in this case. And commutativity is extra. So these three and closure of this plus, that means if x and y are in V, then x plus y will also be in V. So these properties make a group, and extra this property makes it an abelian group. Next is the associativity of the dot. So clearly the dot is from R cross V to V. So it is not closed under this operation. So it is there is no question of dot forming a group with V. But dot also has the associativity property, and this is the multiplicative identity. So in real numbers, we know what exactly is 1. But in a field, we will see the properties of a field. There is always an element which is like 1. That is called the multiplicative identity. Then there is distributivity of dot over plus. We know that. So see, all these properties are very elementary. We know all these properties, but we are now studying them formally. So
ma'am,
this,
is it multiplication also a part of abelian group? Like it is also commutative, right?
it is commutative, but it is not even closed under this operation. It has to be from V cross V to V. So this will not form a group with dot.
Okay.
Ma'am, can you give an example that how multiplication is not closed?
The dot over here is from R cross V to V. If it would be from V cross V to V also, it wouldn't be, because the zero element will not have an inverse.
Oh, okay, ma'am, I understand.
Now, what is this field? Again, it is a need not be. Yeah, it is not actual multiplication. I just want to like set the thing in your mind, because this is a very abstract concept. So field is, again, it is a set with two binary operations, plus and dot. F with plus again forms an abelian group, where 0 is the additive identity. Now, answering this question, dot will also form a group, but with what? With this set F cross, where it is the set of all the non-zero elements of F. Otherwise, R wouldn't form a field, because 0 doesn't have inverse. And as I said, a field will always have a 1-like element, which is the multiplicative identity. And then there is the property of this distributivity of dot over plus. So we can see that R satisfies all these properties. So R is the easiest example to take as of a field to understand what a field is. Other examples, Q, C, will set of irrational numbers form a field? Will irrational numbers also be a field? We can see that R is a field, rational number is a field. So will irrational number also be a field?
This is not close.
I couldn't hear you.
Yes, ma'am.
It will be a field. But do you think 0 is an irrational number?
Ma'am, 0 is in whole numbers, so
But 0 is not
zero.
irrational. So we don't have our additive identity. So irrational number is not a field. But rational number will be a field. You can check all these properties will hold. One more is, have you come across this thing, the integers modulo p in number theory, ZP?
Yes, ma'am.
So it is easy to prove that such a thing Zn will form a field if and only if this n is a prime number. So you can check it from the definition directly. It's an exercise. Now, yeah, it is a field if and only if n is prime. Yes. So here you just replace this lambda. Instead of lambda in R, we will say lambda belongs to a field. So we will say vector space is defined over a field. Now these are two exercises that firstly the zero of a vector space is always unique. The zero element is unique. Why? If you have two such elements 0, 1, 0, 2. So first I use the property that 0, 2 is a zero element. So using the definition 0, 1 plus 0, 2 will be 0, 1. But 0, 1 is also a zero element. So this will also be equal to 0, 2. Hence 0, 1 equal to 0, 2. So 0 is unique. Now this you can prove 0 dot x equal to 0. Now yeah, one more thing is observe that this 0 is not in bold. So this means this is the scalar, the 0 of the field. This 0 is in bold. This x is in bold, which means both these are belonging to the vector space. And you can prove this using this property. Just write the 0 here as 0 plus 0 and you will get this. And also before we used to denote vectors with this, right? But now we shall denote it. In this slide, it has been denoted by bold. If you see bold, it means it's a vector. Otherwise, you denote it with a tilde below V. That is how we represent vector. Okay. Now we will see examples, and if you see these examples, you will realize that we have been dealing with vector spaces since our childhood. It is just that we are formalizing the definitions now. So this example I already gave Rn over R. Also Rn over Q. I already said Q is a field. Now this is something which is not exactly R. It is the set of all polynomials with real coefficients. So just using, we know what addition of two polynomials is, what that means, or multiplying each coefficient with scalar. We can check that all the properties will satisfy just by property of real numbers. Now, as I was saying, this example, solutions of homogeneous linear equation Ax equal to 0. Now we can see why it is a vector space. Firstly, it is a subset of Rn. And yeah, this Mn means set of n cross n real matrices. It can also work with any m cross n. Like in that example we saw, it was not n cross n. It was a 2 cross 3 matrix. So that will also work. But yeah, this has to be 0. Otherwise, it will not be closed under the plus operation. And simply the set of all n cross n real matrices. 0 element is the null matrix. Now, this is one abstract example. So as I said, Rn, we can visualize it as the set of all the functions from the set 1 to n to R. Similarly, we can replace the set 1 to n with any abstract set x. Then we get Rx. So set of functions from x to R. This will also form a vector space. Again, the set of continuous functions from x to R. It's a subset of this, and that will also form a... So why continuous function? You can add them, it will be continuous. The rigorous proofs is done by epsilon delta definition, but we will not do that now. But we all know you all know for a fact that f plus g, if they are continuous, then f plus g will also be continuous. So all these things you can see, it will form a vector space. Now this is the first example we see of a finite field. Till now we were seeing examples of like huge fields like R, C, Q. This is an example of a short sweet field. Z2 is what? 0 and 1, right? So I already said it is a field if and only if this n is a prime. So 2 is a prime, Z2 is a field. 0 and 1. what are, as I said, plus dot need not be the normal plus dot that we know. This is one example. This is a good example that A, B are two subsets of X, and the power set, that is my vector space here, and the field is Z2. So the plus is replaced by union, and the 0 dot A is the null set. This is a 0 element. 1 dot A is A. So it satisfies all the properties. So here we see the magic of mathematics, that this plus and union are completely different things, but they share such similar properties. So are the examples all clear? Why all these form vector spaces? Now to prove that this is a vector space, you need to write down all the axioms, that it satisfies all the axioms. These are some exercises for you to do. So just tell me the answer of this one. Set of irrational numbers over Q. Will that be a vector space? Will set of irrational numbers be vector space over Q? So no, right? As I said, there is no 0 in irrationals. One more such example is this line. It doesn't pass through origin. So there is no 0 vector.
Because the line is also non-homogeneous.
Yeah, that means it is not passing through origin, right? So it doesn't have the 0 vector in it. So it cannot be a vector space. Now, subspace, this new concept, subspace. So the name suggests it is a subset of something. Of what? Of a vector space, which itself forms a vector space. Formally defining, a subset of a vector space is called a subspace if it contains the 0 element and it is closed under the operations plus and dot, which means v1 plus v2 is in S and lambda dot v is in S for all v1, v2 and v in S. So we can see that this means we are saying that S is itself a vector space over the same field, just we are restricting V to S. Now this is an important lemma. It is very helpful in checking if something is a vector space or not, because this is a bit cumbersome to verify like so many properties. So if we just check that for every alpha beta in F and VW in S, if alpha V plus beta W is in S, so then we say it is closed under all linear combinations. So to prove if and only if statements, what do? We prove the if part and the only if part. So firstly, it is non-empty subset. So there is some V naught in S. Then by our condition, if we take VW, both these as V naught, alpha we take as say 0, alpha beta is 0, both these as V naught, then we get our 0 element. First property done. Next one, we take alpha beta 1, then V1 plus V2 is there. For lambda, we take V1, V2, both these as V, and this alpha is lambda, beta is 0, we get lambda V. So the if part is done. Now only if part, we know that S is closed under plus and dot. So closed under dot, so alpha V, beta W are in S. Then closed under plus, so alpha V plus beta W is also in S. The proof is clear, right? So we can just check if this property holds, then it will be a subspace. Now examples, firstly we can see the trivial subspaces, only 0 element and the whole vector space, because the whole vector space is a subset of itself and it is a vector space. Now the line passing through origin in R2. this such a line, it is a subspace of R2, or a plane through the origin in R3. What about a line parallel to this? It is not passing through origin, so it will not form a subspace. Now the next example, we have seen example of RT, set of all polynomials, but now we take set of the polynomials of degree less than equal to n. So that will form a subspace. You add any to n degree polynomials, it will give a polynomial degree less than equal to n. Now the question is, will set of polynomials degree exactly equal to n form a subspace?
No, I guess because of the lack of zero vector.
Yeah, lack of zero vector. You add also 2n degree, it may not give the highest
Yeah,
coefficient.
when we add to that case also fails.
Yes. So this will not. Now this example I already gave, the set of continuous functions from x to r, that is a subset of all functions, and it is a vector space. So this will form a subspace. So these are just examples. You can visualize in R2, R3. Now the question is, so it is easy to see that S intersection T is also a subspace if S and T are subspaces. Why? You just use definition. Take any element in S intersection T, it is in both S and T, so it will satisfy all the properties. So this will also be a subspace. But will the union also be a subspace?
Generally not, maybe a subspace, but generally it's not considered a subspace because the intersection of the force vectors doesn't exist.
Yeah, exactly. So in R2, we can see it very easily. You just take two lines passing through origin, S and T subspaces. Say one vector here, one vector here. What about their sum? Plus is here. No, it is not in the union. So it is not generally a subspace. What if we want to extend this set to make it a subspace? What do we have to do? I said that subspace means it has to be closed under all the linear combinations. So we have to put all the linear combinations of these two lines, of these two vectors, say, and make a subspace. So we put all linear combinations of this, we will get the whole of R2, right? So then we say that these two vectors span R2 or generate R2. In R3, if it would be, then they would form, we know that two non-collinear vectors like this form a plane. And a plane, that is a subspace. So it is spanning or generating this plane. So what do I mean by this span? First, I will formally define linear combination. So it is just summation alpha I vi, where the alpha is belong to F and the vi is belong to V. We already know what linear combination is. Now, what is linear span? For any non-empty subset, mind you, this is not subspace. Any subset A, in R2, we took the example of two non-collinear vectors V1 and V2 like this. So any subset, the linear span of that subset is defined as the set of all the linear combinations of finitely many vectors taken from that. So if we define it using symbols, it is basically this. So the set may not be finite always. Set may have infinitely many elements, but we take the sum of the finitely many vectors, linear combination of finitely many vectors. So first thing to see is that this span of any subset, any set is always, it will be a subspace. Why? Because you take any two linear combinations, add them, it is a linear combination. Next is, it will contain A and is the smallest subspace that contains A. This is just very formally written why span of A is a subspace, but it is basically what I just explained.
Ma'am,
The second,
question there.
yeah.
In the definition 7, we say ki we only combine a number of finite vectors at a time. So what will happen if we try to combine an infinite numbers of vector instead?
The
So,
sum may not be defined. So
So
we
I
cannot
guess so I guess because we cannot define that sum, it will also break the vector space.
what?
Because the sum may not be defined because of the infinite numbers of vectors we are adding at a time, so the vector space may also not be defined, I guess.
No. Vector space can have infinite elements. Like
No,
vector
like,
space.
the definition 7 says ki we can add all your finite number of vectors at a current time, but I am saying ki if we try to add a infinite numbers of vector instead, and does that break the rules of vector space?
No, we are defining linear span as set of linear combinations of finitely many vectors only because we don't know if we take infinitely many vectors it is defined or not. So we cannot give a definition like that. This is a definition of the linear
So,
span.
so it's like uncertain key it will be defined or not defined.
Yeah, obviously, no. If you take, you never know. Infinity is a very fragile thing. So in definitions, we will take finitely many vectors. But that does not need to mean that A has to be a finite set or something. A can be anything.
Okay.
Now the second part of this theorem. So A will obviously contain span of A, right? Because for that is for any V in A, just take finitely many vectors. So take only one vector V, take alpha to be 1. 1 is there in the field. So then V will be in span of A. So trivially A is contained in span A. Why it is the smallest subspace? Suppose there is a subspace which contains A. Then I have to show that that subspace will also contain the span of A. Why? In my lemma 5 was this one. Here we have proved it this for 2 vectors. We can extend it using induction and prove this same thing for n many vectors. Then summation alpha I vi for I 1 to n, this will be in this. So any element of span of A will be contained in a subspace because the subspace is closed under linear combinations. So span of A will be contained in S. So is the proof clear of this theorem? Now examples for a singleton vector, a single vector, the span, like in R2 for example, say only, okay, I will give a better example. Say the j cap vector. What is the span of the j cap vector? The y-axis, right? The entire line, y-axis. So in R2 for a vector, the span of a single vector is that line, entire line. And a vector is always defined to be starting from origin. So that line will always pass through origin. So it will always form a subspace. In Rt set of polynomials, span of polynomials degree less than equal to 1 is 1 and t. So for n, p, n, it will be 1 t, t square up to t to the power n. Now we have a concept of generating and independence. So first, let us define a generating or a spanning set. If the span of A is V, then A is called the generating or the spanning set of V. Like in R2, say we have I cap, J cap and I cap. Does this generate the whole of R2? This generates, right? Y-axis, x-axis. We can write any vector in terms of this. So for R2, the generating set, one such generating set is I cap comma J cap. When will it be a minimal generating set? If there is no proper subset which is also a generating set. Consider I cap J cap. if there is a proper subset of I cap J cap, which is a generating set. Proper subset is what? Either only I cap or only J cap. So only I cap will generate my x axis, only J cap will generate my y axis. So only a single vector cannot generate whole of R2. So I cap J cap, this set is a minimal generating set. In fact, any two vectors which are not collinear in R2, they are independent means they are not collinear. In R3, they are not independent means they are not coplanar. Why? Because if they are coplanar, then they satisfy a plane equation. If they satisfy plane equation, that means they satisfy a linear relation. So then they are linearly dependent. So that is only formally defined here, that a finite collection of vectors is independent, or rather linearly independent, if summation alpha I vi is 0 implies all the alpha i's are 0. And a subset A is called independent if every finite subcollection of the elements from A is independent. So what is the opposite of this? That is linear dependent, which means there exist, this for every will turn into there exist. There exists some alpha I which is not 0, but summation alpha I vi is 0. So some non-trivial linear combination is 0. And independent, we have something called a maximal independent set if there is no independent subset of V properly containing A. Again, take example of I cap J cap. Suppose we take a different vector, say 2I cap plus 3J cap. Something like this. Okay, 2I cap plus 3J cap. So that set I cap J cap 2I cap plus 3J cap, it is clearly not independent, right? In fact, we know I cap J cap, any vector can be written in terms of these two. So if we take any other vector from R2 into the set I cap J cap, it will not remain independent. So we can say I cap J cap, this set is a minimal generating as well as a maximal independent set. For R3, it is I cap, J cap, K cap. So such things are called bases. So I will formally define basis. First, some things about independence which you should note.
Ma'am, a question. As
Yeah.
you said, the minimal generating set is the same as the maximal independent set.
No, it is
So
not the same.
is it not the same? But as you just now you said ki they are almost the same.
No. I am giving I will formally define basis. But right now I gave example of I cap and J cap. It is if it is minimal generating and maximal independent, then it will form basis.
But we can say that minimal generating and maximal independent are equivalent instead of same when they are forming a basis.
Okay, you can try to write it down. Wait. Yeah, so I will come to basis. Just give me 1 minute. First, these are very easy statements which come just from definition, that this such a set, it is not independent if and only if there is some vi which is a linear combination of the other vj's. Then any subset of an independent set is independent. That is, if you just write it down using definition, it is very easy. Now an independent set, no element, if there is 0 in a set, it is not independent. Is that clear? Like, can you all see that easily? If there is 0, then the set cannot be independent. Because if there is 0, then you take any alpha, any non-trivial linear combination will give me 0, because 0 into anything is 0. Now these such things you can just do by writing out the definition. And then if it implies all the alpha is are 0, then it is 0. So is there anything here which is not clear? Then I will explain, or I'll just go to the basis part. So now here about this minimal generating maximal independent thing. If there is a subset,
Ma'am,
yeah,
ma'am, can you please explain how to find that independent set?
okay. Not how to find, like how to check if it is independent.
Yes, ma'am, how to check?
So it is a bit difficult to write here, but yeah, so you do, what is the definition? Summation alpha I vi equal to 0. 1 second. Yeah, so summation alpha I vi is 0. So you take alpha 1 into this plus alpha 2 into this plus alpha 3 into this. So what will you get? First is alpha 1 plus 0 plus 2 alpha 3. So alpha 1 plus 2 alpha 3. Comma, what is here? Alpha 1 minus alpha 1 minus alpha 2. Now alpha 1 plus alpha 2 plus 4 alpha 3. And what do you have here? It is equal to 0. Alpha 1 plus alpha 2 plus 4 alpha 3. So you have now three equations. Three equations, right?
Yes, ma'am.
And
Ma'am, and all three are equal to 0.
yeah, so this is equal to 0, this is equal to 0, this is equal to 0. Now if you solve that equation, will you get alpha 1, alpha 2, alpha 3? Does it have
Yes,
to
ma'am.
imply it is 0? I haven't solved the equation, but
Ma'am, so if any of alphas are 0, then this cannot be an independent.
what?
Ma'am, so if any of the alpha i's are 0, then it cannot be an independent set.
No. If all the alpha i's, if this condition implies all the alpha i's are 0, then it is an independent set. That is my definition, right? Then it is a trivial combination. All the alpha i's are 0.
Ma'am, but what is an independent set? I am not able to understand. I cannot understand.
See, independent set means there is no linear dependence. The definition is this. It is simply this, nothing more and nothing less. It is independent if you take a finite collection, summation alpha I vi equal to 0, that has to imply that all the coefficients are 0. Suppose one of the coefficient is non-zero. Say you have v1 and v2, and say v1 plus 2v2 is 0. This is here the coefficients are not 0, right? If you have an equation like this, then can you say that v1 and v2 are independent? It is clear that they satisfy a linear relation. They are depending on each other. v1 is equal to minus 2v2. You can write v1 in terms of v2. Now, if there is no non-trivial combination, like if summation alpha I vi 0 will automatically imply that every alpha I has to be 0. Like take the example of I cap and j cap. I cap you can write as 1 comma 0 and j cap you can write as 0 comma 1. if you take any combination, say alpha 1 plus alpha 2 0, 1, what will you get? Alpha 1 comma alpha 2 is equal to 0. Does that not imply that alpha 1 and alpha 2 both have to be 0? So then that is why we are saying that I cap, J cap are independent. They are perpendicular, they are independent. The definition, formal definition of independence is this, that you write down summation alpha I vi equal to 0, solve the equation and see if it has to necessarily imply that each alpha I is 0. So is that clear? Is it clear how to do this kind of thing, how to check if it is independent? Yeah, and now someone was asking about this maximal independent, minimal generating. Can you repeat that question once more?
Yeah, ma'am, I was just saying ki, yes, so we can say because there is a basis when because they're all equivalent, not equal. I was just asking that ki minimal generating set and maximal generating set are equivalent, not the same, like because of the basis.
Yeah, actually
And,
it will actually imply that minimal generating implies maximal independence.
and also that if a vector space have a minimal generating set that isn't independent.
No, it will actually imply maximal independence.
And ma'am, can you just slide the last slide, because I guess I was having a doubt in the fourth point. Yeah, the
This
fourth
one?
point. A set
This-
consisting of two vectors is independent. I guess it should be dependent if and only if one of the two vectors is scalar multiple of the other two. Shouldn't that be
A
dependent?
set of two, is this is wrong. I'm so sorry. If it is a scalar multiple, then it is then they are dependent on each other. I'm so
Yeah,
sorry.
I was just confused.
Yeah.
Wrong
I'm
one.
sorry. I'm sorry. Thank you for pointing it out. So now we come to this thing called basis. So it is kind of like a structure which is giving me my whole vector space. The theorem, this is our first non-trivial and the deep theorem, which says that there is a subset which is both independent and generating, and such a see, generating doesn't imply minimal generating. That much we can easily see. But yes, minimal generating does imply maximal independence. So if there is a subset which is both independent and generating, that implies it is a minimal generating and maximal independent set, and such a set is called a basis. Now a basis is not unique. A basis is not, suppose for R2 only, we have the x and y axis I cap, j cap is a basis. Also, if you take any two non-collinear vectors, it will still give me the whole of R2. So the basis is clearly not unique. But can you take less than two vectors or more than two vectors? Will that still be a basis? No, clearly not. So then what do we see? What is unique here? Not the basis, but the cardinality of the basis is unique. Now here I've written bijection because a basis may not be finite. So in case most examples that we will see, the basis is finite, but one example is set of all polynomials. There the basis is not finite. But it is one, I don't know if you know countable, uncountable, the concepts, but the basis is still countable. So it is still better, but there can also be uncountable basis. So cardinality of basis same, cardinality of sets same. It just means that there is a bijection between the sets. In case of a finite basis, we can say that this number, cardinality, this number is unique. And this unique cardinality is what we call the dimension. So we have been loosely saying two-dimensional plane, three-dimensional, but what exactly is our dimension? It is nothing but cardinality of the basis. And one more fact is, any vector can be written as a unique linear combination of the vectors from the basis. Now, before we go into the proof of this theorem, first we will see some examples of basis. Now for R2, R3, we know that the pair 1, 0, 0, 1 or R3 1, 0, 0, 0, 1, 0 and 0, 0, 1, that's I cap, J cap, K cap, that forms a basis. So naturally for Rn, this thing will form a basis where each EI is the n tuple with all zeros. In ith position, I have 1. So for so we can see that the basis has n many vectors, so the dimension of Rn is n. So we have formally, now we can prove why we say it is n dimensional. Now why it is, firstly, independence easy to check. Take summation alpha I ei. Then I've proved for n equal to 2. I proved that before. So we will get summation alpha I ei means we will get just this, all comma, 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 alpha n. So this is 0 implies that each of the alpha i's are 0. So does it implies automatically that each alpha I is 0. So that means that it is independent. Next, what do we have to show? It is generating. So take any vector in the n dimensional in Rn, say alpha 1, alpha 2, alpha n. A vector in Rn looks like this, right? So you can write this vector as summation alpha I ei. So we have shown it is both independent and generating. So that will imply it is minimal generating and maximal independent. You could have also shown that it is only maximal independent, or it is only minimal generating, or you can show it is both generating and independent. So then we can show that this is a basis. So now we know that dimension is n. One more basis, we know basis is not unique. For n greater than 2, we can also prove in the same way that this set will be both independent and generating. And one easy way to check, if you already know the dimension of that particular vector space, then we can see if there are n, if the dimension is n and we have n linearly independent vectors, then we already know it is the maximal independent set. So here we have n vectors. In this case, we just need to show this is linearly independent because we know that the dimension of Rn is n, because we already have one basis here. So all these are easy. Tell me if you don't understand any of these. So yeah, for this vector space, this is a subspace of R3. Homogeneous equation, subspace of R3. How to do these kind of things? This is, we have one equation only. So put Z on this side. Z is equal to minus X minus Y. So we have two independent variables, one dependent variable. So intuitively, I can feel that the dimension should be 2, right? So just for making things easy to form one basis, how do you do? Take X as 1, Y as 0, X as 1, Y as 0, Z is minus 1. Take X as 0, Y as 1, Z is minus 1. Done. The dimension is 2. And you can form many other bases. Now, should I give the proof of this? I'm not sure if there is time. Like the first two parts are not difficult. Suppose the idea is basically, we first start with, firstly, we cannot do it for infinite dimension right now. So we will do it for finite dimension only. So my assumption is only that there is a finite generating set. There is a finite generating set. There will always be a generating set because the entire vector space itself is a generating set. There will always be a generating set. But we assume it is finite. For infinite, we need other things like axiom of choice, Zorn's lemma. So we cannot do it at this level. But so we start with finite generating set. Say this is a finite generating set. Then what do? We discard the superfluous vectors, which means we discard those vectors which are linearly dependent. Suppose this set is not independent. Then there is some Vi which is a linear combination of the other Vj's. So we just discard that. The span still remains the same because that was just linearly dependent. Suppose I cap, j cap, 2i cap plus 3j cap. We discard 2i cap plus 3j cap. The span is still R2. So like that, we are reducing the set without changing its span till it becomes an independent set. Then we get both independent and generating. So that proves the first. Next, we show if it is both independent and generating, then it will be minimal generating and maximal independent. Suppose there is another independent set which strictly contains B, that means it is not maximal independent. Then there are some vectors which are not there in B. Then none of these vectors can be in the span of B because this entire set is independent. But we took the assumption that B is also a generating set. Then that is a contradiction, right? If W1 is not in span of B, or if any of these vectors are not in span of B, then it is clearly a contradiction because B is supposed to be a generating set. So it is a maximal independent. Next, if there is a proper subset of B which is generating, then this set B minus C, this is non-empty. So take some element in this. Then B is in the span of C because C is generating. Then if B is in span of C, then C union B is not independent. But C union B is a subset of B which is independent according to our assumption. So this is also a contradiction. So it has to be maximal independent and minimal generating. Now for this third proof, this third part, we need something called Steiny's exchange lemma. So it is something like this. This is the algorithm. So first, we take any two such bases, B and B prime, M vectors, N vectors. So both these satisfy the property of minimal generating and maximal independent. But now we have to show that M is equal to N. So what the idea is, we take one vector W1, we put one vector from B prime, put it into B, and discard one vector from B. So we put W1 in B, then this set W1 union B, it is not independent, right? Why is it not independent? Because we had started with the assumption that B is maximal independent. So we include one vector, it will not remain independent anymore. But it is still generating because it was minimal generating. Hence, there are non-zero, not all zero, such scalars are there, such that the linear combination of this is zero by definition of linear dependence. Now, what if all the Ci's here would be zero? Then this is zero. That would imply that CW1 is zero, which implies that W1 is zero. But W1 is not zero because this is an independent set. So what does that mean? One of the Ci's, from here only, one of these have to be non-zero. So what does that mean? That one of the Vi's is a linear combination of W1 and the rest of the Vj's. So we drop that that particular vi. Still we get a generating set. So we call B1 as this set, where we have discarded V1 and taken in W1. So it is still independent and it is still generating. Then we do the same thing. We put in W2 and discard one of the VIs. Like this, we will go like this. This algorithm will keep following till we have dropped at least n distinct elements from B. So that means, what does that mean? We are dropping each 111 element. So that means that M cardinality of B is greater than equal to the cardinality of B prime. So M is greater than equal to N. Now do the same thing, except now you interchange B and B prime. So now you put V in this, discard W from this. Then we get N greater than equal to M. So that implies that N is equal to M. So is this proof clear? It might be a bit complicated because there is, but once you understand the algorithm, then it is very clear as to why it is working and why it is happening. But once again, it cannot be done for infinite dimension right now because we still need this Mn as like numbers. So for infinite dimension, we don't learn that in B.Math first year also. So we have also proved it only for for finite dimension. So I hope that everything is clear. If you want more reference, then these are some books. Hoffman and Kunz is a very classic book, and A.R. Rao and P. Bhimshankaran. This is a very elementary book. Like everything is explained clearly, examples, very good examples are given, and there are a lot of exercises. So you can follow any of these books. And if there are any questions, this is my mail ID. You can ask. Are there any questions? Yeah.
Ma'am, actually, I had joined this camp today only, so this meeting is recorded, so we will get recording. Or
Yeah,
this
you will
PDF.
get recording. Shubhajita will share. And if you want, I can share the slide also.
Ma'am, a question is there. Just when you were telling us the examples of the bases in that side, there was a exercise of the second exercise of the cyclic vectors. So doesn't it set actually fail to be an basis if the n is an even number? Because if n is even, then all the alternating v1 v plus v2 minus v3 plus v4 minus, that way everything cancels out and becomes 0, something like that.
I haven't checked it. You can check with, for n2 it will obviously not work because it is e1 plus e2. That's why I've written n greater than 2. You
No, I'm saying for if n is even, then
Mhm.
I'm saying for that. I checked it for n odd, it's coming out perfectly on, but for n even, it's coming out as an 0.
And even what is the problem?
And even if we're trying, then the alter, because we're taking v1 equals to e1 plus e2, v2 equals to e2 plus e3, that way we are taking. No, so when we are taking n equals to even, then all the alternates are crossing out, cancel it.
Will it be, it will be independent still, right? C1.
If
I'm
it
not
cancels
understanding
out
what
with,
is the problem.
No, like if the n is even, so when they are cancel outing the alternating sums of v1 minus v2 plus v3, then it's coming out 0. So when it is 0, the set must be linearly dependent.
It is not independent, you're saying.
Yeah, if n is even.
Might be. I haven't checked actually.
I had one more question on the zero vector thing. So so when you're telling us about the zero vector, I had a question, but I couldn't ask at that time. So is it like key
Which zero? Which part?
zero
Zero
vector?
vector. about dependence or
About key, it's all I'm actually about the concept only. So when you are looking at a zero vector, we are saying that it there is a zero vector, it's automatically becomes a dependent.
Hmm.
So if the and we are saying it is a dependent when there is a zero vector, so we can also say the opposite of that. It's dependent, so it must be hiding a zero vector.
no, not necessary.
So is it?
I cap.
It's not necessary.
No. See, take say I cap and 2 I cap. Just take a scalar multiple of any non-zero vector. It is still a dependent set, but it doesn't have zero.
Okay, and one more thing was on key vector space have a set of independent vectors, many sets. That so
What?
a vector space have a set of independent vectors and a set of dependent vectors. So is that possible that a set of independent vectors in a vector space is larger than the set of vectors that spans in that space, like that is there in the space, or the spanning all set is always bigger, or a fixed thing it will be bigger than the number of sets of independent vectors, and the number of independent vectors will always be dependent on the spanning.
I didn't get your question.
So I was asking, curve vector space have two parts of set of independent vectors and set of dependent vectors, right?
Like there are sets which are independent, there are sets
Yeah,
which
and
are
there are sets of which are dependent. Yeah, right. So I was just asking key the number of independent vectors in a vector space depends on the number the larger number of all the vectors in that space, or is it independent of that?
the number of independent vectors.
Yeah, in that particular vector space.
A vector space which has dimension n, say, it cannot have more than n independent vectors.
Okay, I was just asking that.
Otherwise, basis is maximal independent, right? So you cannot have n plus 1 independent vectors. I don't know about the recordings that Shubhajit Da will know.
Ma'am, and this slide, will you share with us?
Yeah, I'll share.
The slides and the talk will be shared to everyone after the camp is over.
Oh,
We'll
okay.
try to do it as quickly as possible. But yeah, it will take some time from our
So
end.
it will be shared in the mail only where we received the schedule.
No. The slides for the talk will be shared in the mail, but the recordings of the talks will be shared on the YouTube channel that of a limit camp. That is it.
Okay.
One more, just last question, if you don't
Mhm.
mind.
Yeah, sure.
Yeah,
Since
you can.
a vector space can have infinitely many number of bases,
Yeah, vector space can have a lot of bases.
so does a vector actually possess an absolute identity of its own, or is a vector entirely defined by the specific coordinate system we try to look through it or choose?
If we have a, when we have a basis, any vector is uniquely defined by the vectors in the basis.
Okay.
Okay, so anyone with any other doubts or any questions for the speaker, or we can thank our speaker for the talk. Okay, so thank you, Srijani, for the talk. We can end this meeting here. Thanks.